Okay, and I also do that, but I don't have chocolate today. Okay, and ask stupid question also. Anyway, all questions sometimes are stupid because you don't know what it is. So many people, don't ask questions because you think it is a stupid question, but otherwise you will never learn. Okay, so you can ask me anything today. If I know, I'll answer. Okay, because I also don't know many things because scientists are also struggling to understand the universe. Yes. Okay. Good. In fact, it's a joke. When I started my PhD 2002, we thought that we understand 90% of the universe. 10% was unknown. Now, after 20 years of research, we came to know that we only understand 4% of the universe. So, the more we are learning, the unknown is becoming bigger. So, don't worry to ask stupid questions. Okay, good. So, first one, the universe in cosmology, we tell that it is a history of space and time. So what is space? Anybody can answer? In this room, if you remove everything, including my body, chair, your body, everything, what remains, that emptiness is space. Yes? The thing is, this emptiness, space, was not there in the beginning. So you are already like, oh, what do you talk about? So even this empty space where I am moving my hand, it got created 14 billion years back. And then was the space and both time came into existence 14 billion years back. So then don't ask me the question what was before that. Okay, nobody knows. Okay, but it is true that we know that it was not there before that. Something gave rise to space and space and time is our home. Then atoms, molecules, all these things I'll talk today. How then first star formed and then life came much later. Clear? So this study is called cosmology. Okay, so today I'll not go that much into the technical thing because it's two lectures. So first half I'll show some video, some animation, and then next half I'll do little bit of simple mathematics with your Newton's law, with your simple thermodynamics. You can do it. Okay, good. So now actually the many things did not work here, but it's okay. So this is the picture of the Empire State Building in New York. When I was there, that was the highest building because 9/11 Twin Tower was gone. So I did PhD here. So if you squeeze this whole Empire State Building, 87 floor building, into, suppose there are space between atoms and molecules, right? If you squeeze totally, then what it will happen? This did not come here in the video somehow in the picture. It will become just a rice grain. So basically all you see, even the solid stuff, Mysore University, basically space is everywhere. Getting it? If you squeeze it, it becomes a rice grain. And I'll just tell you, it is not part of the talk later. If you squeeze the whole earth, it will become a matchbox. And if you squeeze the whole sun, it will become 10-kilometer radius. And that is called black hole. Getting it? When you squeeze the space, squeeze everything in between and then clump them more and more atom crashes, and then you cannot crash anymore there, that becomes a black hole. So even if you can create from earth, you can create a black hole if it is squeezed. And that phenomena actually happens in the universe. When a star dies, if mass is more than 1.4 solar mass, then it turns into black hole. So that same thing happens. So space is abundant in the universe, and that's what got created in the beginning. Now, this empty space, this is Einstein and this is Hubble. So Hubble is known for discovering that the space is actually expanding. Which means what? Because you cannot observe space directly. Can you see space? If space expands in this room, you cannot see it unless you see everything in the space is expanding. Getting it? So Hubble, he was an astronomer. He looked in different direction and he saw that every stars is going away from each other. If in one direction it is going away, that means it's some local dynamics. But everywhere, from every place he looked into it, and everything is going away from each other. Then he said that it is only possible if space itself is expanding. That's what when Hubble told, then Einstein was really confused. Einstein believed in a static eternal universe, means it is there for ever. Because if space is expanding, that means if you go back in time, this is the just a picture, space is expanding, this is expansion. And if you go back in time, then there will be an one point when they were at a point. When you come to a point, then space does not have any significance. Space means some volume is needed, right? So this point, because if it is expanding universe, if you go back in time, then you will hit a term called singularity. Singularity means where you cannot define mathematically what is space, what is time, everything, that is called Big Bang. And we don't know that what happens at t equals to 0, but from nanosecond after till today, we have pretty good idea. There are some mysteries which is unexplained, but more or less we know that from nanosecond after universe, what are the milestone which has happened, and today we are here. Okay, this took 14 billion years. 1 billion means 10 to the power 9. Okay, so 14 billion years it took, and this study is called cosmology. So I'll tell you few milestones. Those are so important, because without that you will not even form planet, stars, anything. Okay, so that will come slowly, but mathematically with simulation we can actually generate. This is not from observation, this is from computer simulation. You can actually generate all the stars, galaxies, everything in the universe in supercomputing. In IIA also we do. Okay, starting from here we see the galaxies form, and in the beginning there was no space time, and then the atom came, and then first hydrogen atom formed, and then I tell you what has happened, and that is the history of the universe called cosmology. So before we go there, right now the size of the universe is very big. Very big means actually very big. This much light years, 30 billion light years. If you turn it into miles or kilometer, you can see how many zeros are there. So it's huge, our universe. Okay, and 1 light year is 6 into 10 to the power 12 miles. And universe is 30 billion light years. So 30 into 10 to the power 9 times 6 into 10 to the power 12 miles is our universe. So it's huge. Even our galaxy is very even a dot in this universe. So space-wise is huge. Now the question is, how many of you have asked this question, that whether the universe is infinite or finite? I'll take a vote. How many of you think that space has a boundary? Or no boundary? You can just raise your hand. How many of you think that if you have boundary or no boundary? No boundary. So it will go forever. Anybody else? Everybody else from the back? No boundary? How many for no boundary? That it will be infinite. And how many think that there is a boundary? 1. Anybody else? See, if space started expanding from Big Bang, then it cannot go to infinite distance. It is traveling, no? So it has a boundary. But we don't know what is beyond that. Because this boundary is so big, no instrument can tell that what is. But space has a boundary. Because it started from Big Bang and then it started expanding. So if a car moves, it cannot go to infinite distance. It might be very big, but it is still calculable. Getting it? So we know that is what the boundary of the space. This much light years. But we have no instrument which can probe beyond that. And that is not only instrument problem, that is from Einstein's special theory of relativity. After this distance, the space moves faster than speed of light. So if something moves faster than speed of light, you cannot get light from there. Getting it? Yes? Making sense? Because light is traveling in c, but space is going faster than c. That's why you cannot see that. So that's why the answer is, after today's talk, you can tell that universe might be finite or infinite, we don't know, but our observable universe is finite. Getting it? So this is first one about space. Now, there are 2 axioms in cosmology, which is still now we know it's true. One is homogeneous. You have heard the word homogeneous. It is same everywhere. If you go millions of light years away, if you look into the universe, you will exactly see what you see from here. So there we are not at a special point. Okay, a universe is homogeneous and isotropic. Isotropic means any direction you look the same, you see the same. Of course, in solar system is not the universe because you have to see the universe in a very big scale. That is called cosmology, and I am coming to that. This is what universe looks like, and here one dot is our Virgo cluster. Getting it? So now you know how big you are. Okay. So it's huge, and still we don't know what is beyond that. This is 3000 megaparsec scale. Beyond that, we don't know that because there is no light can come from there. So this is our visible universe. In fact, now the most modern theory says there are multiverses like this. There are many bubbles with many stars, many life in there. Forget about in our universe, we might find the extraterrestrial thing. No, already JWST has found their water-like, ocean-like things. So we definitely we are not alone, but we have not found any sign of life yet in other planets. But definitely there are other universes, and each universe has their big bang. At the end, I will show you. So we are in a multiverse, though it is not proved yet, but string theory or the most modern cosmology theory need multiverse to explain certain things, which I will tell you later. Okay. So now, this is what the space expansion is happening. So now I have a question. You are from physics. So suppose I draw a grid in an expanding balloon, and I give them point x1, y1, z1, x2, y2, z2. So if the universe expands and you tell your computer to find the distance between 2 points. So I take 2 points, say this point and this point. This one is x1, y1, z1, this is x2, y2, z2. So what is the distance? X1 minus x2 square. Now the universe is expanding. Still the point remains the same. So if you tell your computer what is the new distance, what it will find? Same. But actually the distance is same or not? It has changed. So normal Cartesian coordinate thing does not work for expanding universe. The distance we know ds square is equal to x1 minus x2 whole square plus y0. That does not work. You have to multiply with a factor called at because that is function of time. So in universe, distance is at square. Distance square is at square. Then x1 minus x2 square plus y0. Is it clear? This at was 0 in the Big Bang. So that's why you don't find any distance. Is it clear? And then at is changing as the universe is expanding. We measure that at from observation. That how that is called scale factor of the universe. That means you can think that how the grids are becoming bigger and bigger and bigger. Okay.
But along with that at also, again that will be same only. That at whole square minus distance square is 8. We call that space time interval. But again it's going to be invariant.
No, that will be invariant, but the space will not be invariant. Space time together is invariant. Yeah. But space distance you will get because A you measure today and you measure after 5 days, then at value has changed. No? So you get a higher factor in front of your distance. So distance will become bigger. Yes. So now here it is. So now I am coming a little bit deeper into the thing. So if today we are here, then you go back 1 billion years, universe was smaller, little bit more smaller, little bit more smaller, and you hit the singularity. Now, from here we cannot speak what has happened, but after nanosecond, we can speak. Because nobody knows, because you cannot do any physics there, because the distance is not there, no coordinates are there. To write any equation, you need at least space and time, isn't it? Even write Newton's law, d2x, dt2 is you need time and space, but that is not there. Then how can you do physics there? So that's why if somebody asks what is Big Bang, don't tell that at time t equals to 0, there was an explosion. That is what everybody says, because we don't know what was there at t equals to 0. So Big Bang is not that there was an explosion. Big Bang means after t equals to 0, we found that universe is expanding and very hot. Very hot plasma. Okay, that is Big Bang. But don't say that at time t equals to 0, there was a blast. No such thing we don't know, because t is equal to 0, nobody knows what has happened. Is it clear? Because everything breaks down there. So that is called, one of the Stephen Hawking tried to go pass here before time and space, but he gave an idea, but it did not work. So it's very hard. Okay. Another idea is, maybe before that there was a universe which was contracting. That is called cyclic universe. Before, so maybe our universe is expanding now, and maybe at some point it will stop and it will contract. And contract, hit a singularity and then again expand. So then you get like a cyclic eternal universe. But even that theory, that universe contract and goes into another expansion, is very hard. One professor from Princeton, I know him when I was there, he was spending 40 years. He has published many papers, but there was a problem, because once you transit from this x equals to 0, many unknown things are there. No, you cannot do. So he could not match the observed universe totally. So that's why his theory also failed. So we don't know actually what was there. Okay. Now I am coming to the normal modern physics, class 10-12. So one question before we go towards the end, I will show you that we know that what has happened from 14 billion years, pretty much. But what is our destiny? It is still unknown. There are some speculation, 2-3 choices are there, and next 10 years experiment will tell that what will happen to us. Okay, whether universe, I'll tell you later. Now it is a secret. Okay, I should not tell now. Okay, so now this is the brief history of time. Stephen Hawking wrote a book. Okay, it's a very famous book. Yeah, you heard about it? How many of you have? So, brief history of time is, after the Big Bang, 3 minutes after the Big Bang. As by the way, from where this proton, neutron came, I skipped it. Basically, after the explosion, there is no such explosion. After the Big Bang, there is this unknown energy, we call it inflaton. Why we call it inflaton? Because universe was inflating. That unknown energy, it is like, have you heard about Higgs boson, God particle? So we call it, I also work on that. Like that, another particle called inflaton, we did not detect it. It's a scalar particle, and that, in a fraction of a second, that actually creates all the neutron, all the quarks, everything. That is called, there is a theory of it, and there is a simulation. We actually create all particles from fraction of a second from that unknown thing. It is not just, I am just telling philosophically, people have spent their whole life writing computer code that from inflaton, how you can, using advanced quantum mechanics, you can create quarks, electrons, all the particles. Okay. So now suppose you got it. Now the first 3 minutes, after first 3 minutes, the neutron and proton combine. Before that, the energy was so high, you know what is inside an atom now. Nucleus is neutron and proton. But even if you make them very high energetic, the neutron and proton will also, that was the energy there. First 3 minutes, the neutron and proton cannot combine. And as the universe expands, universe cools down like a normal gas. You know, and once it cools down, after 3 minutes, we calculated, the cosmologists, this reaction happens, 2 hydrogen, and then proton comes, and then that 2 hydrogen combines with another neutron. This is what exactly called fusion. These things happen, then 3 hydrogen, and 3 hydrogen again matches proton, and then 4 helium. This 4 helium is the stable one, and we predicted, means cosmologists, not me, that we will see 75% of the helium in the sky, intergalactic medium, and 25% will be the hydrogen. That is the main constituent, and exactly we measured, and exactly the ratio is that 75%. If you go to intergalactic media, you will see the helium and hydrogen ratio is 3:1. So that is the power of physics. From Big Bang cosmology, you do all this nuclear reaction, and you tell how much helium and how much hydrogen you will get, and that exactly matched. So then people started believing first time, oh, there might be a Big Bang, because his prediction is matching. In the sky, you match them. Now, the second miraculous thing happened is called fossil radiation. It's called cosmic microwave background. Everybody has heard about fossil radiation? No. So it is very simple. Universe, in class 12, have you read what is the first orbit energy of hydrogen? How much electron volt? That's the exam point you get and you crack the class 12 modern physics. 30.6. You all remember? That means if your photon has energy more than 13.6 electron volt, it will hit the electron and knock out the electron, and atoms will be ionized. So it will be nucleus with a positive charge and electron negative charge. That was the case from Big Bang to 0.3 million years. Because we now know exactly from our physics theory that what is the relation between time and temperature. Because as I say, as you spend more time, universe expand more and temperature should drop. So there is an exact plot between time and temperature. And temperature in different unit we can write. Kelvin, right? You can also write temperature in electron volt, natural units. Okay? Because in natural units, energy is equal to mass, and all these things are there. Have you heard about natural units? In there, C, Goldbach constant, and these things are all one. I'll not go into the detail. So now, you calculate that when is the temperature of the universe is of the order of 13.6 electron volt. Then, if you wait longer, then what will happen? Temperature will drop below 13.6. After that, will the photon be able to ionize the atom? No, because photon has energy less than 13.6 electron volt. Then first neutral hydrogen atom was formed. Before that, it was a plasma photon interacting with electron. Anytime it's a random process. Anytime in some part electron and proton combine, the nucleus combine, suddenly a photon comes, knock it out. So it is a random walk, So photon was also not able to travel freely. Because to travel freely from here to walk to the clock tower, if there are a huge crowd, you will not be able to go to clock tower so easily. Every time you hit somebody. So that was the case for photon also. Light was not able to travel because it was colliding with electron every time. Because it's a very dense universe. Making sense? After 30.6 electron volt or 0.3 million years, that photon which got released is still coming to us. And this is a miraculous discovery. I'll show you. They were not the physicists who got the Nobel Prize for discovering this. They are actually antenna engineer, radio engineer in Princeton. I'll tell you the picture, then you'll know. And then after this is the glow of the fossil radiation. From there, light is coming to us today. See, our universe is very interesting. If you see Somnath's interview, he just ex-director, ex-chairman. He says, suppose we are talking now, the photon is coming and reflecting and going. This photon you can never stop photon. You know that? Photon will always travel in the speed of, and this can travel for millions years if there is free space. And if the aliens are there, they will be able to see that me and you are giving lecture after millions of years. Because if the photon gets reflected, it will have all the images from you. That's what is happening. The light we are seeing now, they are very old. Getting it? So the photon which was released after 0.3 million years is still in the universe traveling. And we saw them and we realized that after seeing them, we saw exactly the spectral distribution, black body radiation of this photon matches with the temperature which was 13.6 electron volt. So, and that took, so today universe is 14 billion years and this happened 0.3 million years. That's why it is called baby universe, because 14 billion years is much higher than 0.3 million years. Million means 10 to the power 6 and billion is 10 to the power 9. That's why we call the fossil radiation of the Big Bang, blow up of Big Bang. Because 0.3 billion years is almost close to Big Bang compared to 14 billion years. So this is astonishing that today even the CMB antenna seeing this history, because the light carry the information. So there is the past is not gone, it is here. Getting it? 14 million years back, what has happened you are seeing now? And we have the CMB has the map, the Planck satellite has created the map, but I'll show you that. But after that, now, after the first star were born, that happened 350 million years later. Because see, to make star, you have to clump all the atoms. Getting it? So first the atoms got created, neutral hydrogen got created, 0.3 million years, and then they are all distributed homogeneously. I said universe is homogeneous. Then slowly gravity clump them. And it is not easy to clump hot gases. Getting it? So universe has to cool down, then only gravity can clump, and the first star formed 350 million years later. Then once the star is formed, that becomes the kitchen of the periodic table. Because universe gave first 3 minutes hydrogen and helium, and little bit of lithium. These are the three things. Then universe says, okay, next 350 million years, let the star form, and inside the star, the fusion reaction happens, and the higher atomic, all the things you know about periodic table, everything is made in the star. So that are the reaction in the star. Stars make first carbon, then higher nitrogen, then oxygen, and all other elements get formed. And once the star form and then they burst into supernova, these higher elements, carbons, everything is thrown. In fact, the carbon we need from life, it was thrown to us by supernova burst. And supernova means it's a dead star. Getting it? So stars book the carbon and it is thrown into the intergalactic media because when it bursts, supernova burst, and then we get it. Even all the elements in your body is cooked in the stars, and it got burst and came to planet. So it is amazing. That's why there is a book because we are all made of stardust. The dust of the stars. Getting it? So now you got the idea that today you came to know that how hydrogen atom formed and the beginning helium formed, and hydrogen atom means the ionized hydrogen was formed much before, but the first neutral hydrogen from 0.3 million years, then fast stars and all these things formed. This is called, there is a stellar physics, you can learn it in any book or YouTube lectures are there. How the fusion reactions create in the stars and give rise to periodic table. Clear? Getting it? Very nice. So now I'll come to till now it is okay, or I am going fast. Okay? You are simple physics, no? I am not going into any technical thing. Now this is what I already told you. T greater than 13.6 electron volt, it was ionized plasma. It's all ionized. And then temperature dropped and the first hydrogen atom. This is called cosmic microwave background. And then atoms form and the photons do not interact with the atoms anymore because it cannot ionize. In quantum physics, if you don't exchange energy, that means you don't talk to each other. So once it cannot ionize, that means their photon is oblivious to the atoms because it will just move freely. It is not plasma and it is traveling. And this is the WMAP or the Planck satellite which actually measured this universe at 0.3 million years by the cosmic, because once the photon gets released, it takes a picture of that time. Getting it? To see the picture, you need the photon. Right? Now this is the story who got Nobel Prize. So these two engineers, they were looking for this is that time radio antenna, and they pointed out looking for some signal, radio signal from the nearby. There are radio waves coming, or they were looking for something. I don't know what they were looking for, but they found a radio wave which, the wavelength you can transfer into frequency and you can transfer into temperature also. Getting it? And they found a 2.725 Kelvin, which belongs to actually radio waves, millimeter. And this temperature wave, they thought that it is coming from local, some stars, anything can give radio. And but they were very surprised that continuously is coming. Because sometimes it comes like a flash, continuously it's coming, and then they change the direction. in the empty sky where there is no star, they saw it is coming. Then they were confused. They said, like, maybe there is a problem in Princeton in US. They went to California by 6 hours flight and did the experiment. They saw it is coming. Then they changed the continent. It is coming. That means they said, like, if it is coming from all directions, then it is not coming from the stars or something. It is coming from something else. Then they started speaking to their colleagues that what is this? We are getting it. Then people found out that there is a model of hot Big Bang cosmology. It says that when universe was 13.6 electron volt, that time the temperature was 300 Kelvin, 3000 Kelvin, and as the universe expand from that time till 14 billion years, they exactly calculated that if in future Big Bang is true, if Big Bang is true, in future scientists will find there is a fossil radiation from everywhere 2.7 Kelvin. They wrote in the book, and that is what Princeton engineers exactly found. Then they got the Nobel Prize, and people really started believing that actually we came from hot Big Bang plasma. Getting it? Actually, there was nothing in the beginning. Actually, there was no atoms, no stars. It's not easy to see that. When Einstein was looking at the star, he said like this is forever. But it came from nothing, and mostly, we believe, mostly it will end up in nothing. Okay. That's what I'll show you in the end. Okay. Very nice. So now, this is the slice. I am cutting now the time into the slice. So this is how the time is running. This is the Big Bang. Sorry, this is why the time is 0 here. So 0 means almost 0.3 million years, because compared to billion years, 0 is close to million. This is the cosmic microwave background, that fossil radiation seen by Planck satellite. Okay. These colors they did not see. These colors means there is some fluctuations in temperature. Mean temperature is 2.3 Kelvin exactly. And then there was after 0.3 million year, you see the first star formed. These are the first star, and it is everywhere because time is running back. So once it form here, it will form here, it will form here, it will form here, because the universe is homogeneous and isotropic. There is a little dark patch. You see, there is a gap between CMB, cosmic microwave background, and the fast stars. This gap is called dark age. That is the where the universe took time to form the fast star. Because unless the star is formed, you cannot see anything. Because you cannot see photon directly. Okay, getting it? Photon gets reflected image, then you see. So then this gap is called cosmic dark ages, and the first fireworks or the first firecrackers happens. No? It happens when the stars formed after 250 million years. So from here to 250 million years, this dark age, till now it is unknown what has happened there. India is building an instrument, it's called SCAR, Square Kilometer Array, with Australia and South Africa and this thing, radio antenna. Because all the wavelengths released here, I told you, from early universe, it belongs to radio wavelengths. Why? Because see, you can calculate the wavelength of the photon from 13.6 electron volt. You all know that, no? But as the universe expands, the wavelengths also get stretched. Anything gets stretched because space is expanding. So if wavelength gets bigger, its energy will reduce or increase? It will reduce. That's why initially it was 3000 Kelvin, but today when you observe it here, it is 2.3 Kelvin. We know that 1000 times universe, the wavelength has been expanded, because universe has been expanded by 1000 times from here to here, because space is expanding. That also we exactly calculate. Okay. So now, after faster, then the life came, or planet Earth came 4 billion years back. Okay, so today we are 14, so around 10 billion the planet Earth came. And the life came much later. Okay, getting it? So universe has waited so long for at least life to appear in planet Earth. So, okay, getting it? So it's very beautiful to see, and today being here we are asking this question, that what is our destiny, what is our origin, what is the purpose? Getting it? So that's the beautiful picture of the size of the universe. Now I'll go into the detail that what are there in the universe. So you'll be amazed to know That till now, all the visible matter means quarks, atoms, all the stars, galaxies, gas, everything is only 5% of the universe or 4%. We came to know that there are two more things. One is called dark matter, that is 25%, and 70% is dark energy, which is like an iceberg. When the Titanic hit the thing, in below there was huge iceberg. They didn't see it. Getting like that, 4% of the universe, we have been looking into the telescope, how billions of galaxies. You saw, no? I show you the homogeneous universe, Milky Way, and we have the Virgo cluster here. This is only 5%. That was I tell in the beginning. Because when I started my PhD, this dark energy part people did not know. So people thought only universe means this dark matter and this. So we thought only this part we don't know. But now we realize that we don't know the whole thing, the 70%. So we only know the 4%, 5% of the universe. That also we totally don't know. Okay. So now, but still, how do we know that it exists? Because if we don't know at all, then we cannot say they exist. No? That I will tell you. It's very simple. So these are the two questions. I work on these things. What is dark matter and what is dark energy? They are the 95% of the universe. And if they are not there, you will not be here. Okay. Without dark matter, you cannot make any galaxy. And dark matter is what? It is some form of matter but beyond our periodic table. Not anything in our periodic table. Not quark, not electron, nothing. All the particles we know, it is not any of them. But it is there because how do we know it is there? Because if there are particles, if they have a mass, if they have mass, they will have gravity. And that gravity will make, that if there is more gravity, there will be more centripetal force, isn't it? And if the sun's mass is bigger, then it will make the planet go faster, isn't it? So we know that there is mass, and that I will tell you from the next picture. This and this. So this is the present day conclusion of the state of that conclusion that what is universe is made up of. So I said this part up to this dark energy, which you don't know. Okay, then dark matter, this part. So only remaining part is this red, blue, and green here. Red is our visible matter, and green is called neutrino. Neutrino is another fundamental particle. Okay, we also don't know that how neutrino get mass, unknown. And then the blue is some heavy elements from Big Bang. Okay, so 0.03%. Anyway, these are all visible part only. So this major part is unknown. Now I'll tell you how did we know that there is dark matter. So this was a Vera Rubin, astronomer. He first predicted that there will be dark matter. She first predicted that there will be. She was a very passionate astronomer. And what she did, that she measured the velocity of this rotating gas in our galaxy. That gases are rotating because galaxy is not fixed. You know that it is rotating? Yes. And inside, what is that? Anybody know? Yeah, it's called supermassive black hole, which we have detected, and that also got Nobel Prize 4 years back. Okay, Event Horizon Telescope has detected that huge 10 to the power 6 times the mass of the sun. A black hole is hiding, and because of that, 500 billion stars are rotating, and we are actually here. We are not at the close to the center. There is a T-shirt people wear. There is a dot here and say you are here. So right now you are here, and there are 500 billion suns are rotating. Okay. So even if you are not working in cosmology, but after today's I give this. This is not this. I give some lecture as I told in the villages. They keep messaging me that sir, I don't understand this thing, but after hearing the talk last 7 days, I am so happy because once you realize that you are here and you are just a dot out of 500 million suns, and life may be there in other planets, so huge. And these galaxy numbers are not one. There are billions of such Milky Way galaxies in the universe, and they are in the galaxy cluster. So now you know that how small, tiny we are. And now anyway, Vidarubin was observing the rotation. You can do that. Even in IIA, scientists do that. This rotation speed as a function of distance. Now, when the visible matter ends, then if you go further, your rotation speed should fall because there is not enough matter. Getting it? In fact, if you do today, I'll show you maybe if we have time. Simple centrifugal force. With that, you can derive that the rotation velocity should go up first until the edge of the galaxy, and then it should fall as you come. So if you measure here, it should fall off. But the observers found that it goes up. That is true. That is good. But it is not falling. It is becoming constant. That means there are some matter hidden, which Vera Rubin first told that is there anything unseen in the galaxy? What is holding that together? And today we know from computer simulation, just by Newton's law, we do the simulation. It's called n-body simulation. We know that without the dark matter, you cannot make this visible matter stay. It will disrupt because it is rotating, no? And you need the collective gravity to make them polarized. So your existence belongs to the dark matter, but which is hidden. And now this is a picture. This is the picture of India from International Space Station. Okay, and this is the computer simulation of our universe. Okay, and you see that these yellow things are actually clump of dark matter. More dark matter is there. So it's very similar. And this is what exactly is our galaxy. I did not show you in the last picture that the blue shadow you can see. It's actually a sphere. And galaxy is a disk. This sphere is called dark matter halo. It is like an egg, but inside there is a disk, which you only see. But this whole halo, it goes 200 times, 20 times more than this visible matter's radius. So our galaxy is much bigger than what we see. And this is all dark matter. It is also going through the visible also. It is also clumped in the center, everything. But here visible is light, so that's why you don't see them, the blue part. So now this part is 25%. 5% is this. But we don't know what it is made up of. So I worked on searching for dark matter during my PhD. So suppose you have lost a key, but you have to find it where it is. For that you need lamppost, because without light you cannot search the key. But this lamppost is based on the assumption that mostly my key is lost here, that's why this lamppost may help. But if you lost your key here and there is no light, then you will not find it. There was a story, beautiful story of Nasiruddin. In my childhood I heard. So Nasiruddin lost his key and he was finding under the lamppost and he was not finding the key. His friend said, "Are you sure that you have lost the key here? You are not finding?" Then he said, "Yes, I am sure that I did not lose it here. I lose it in my home." But they said, "Then why you are searching here?" Well, because there is light here. There is load sitting in my home. So our dark matter search can be exactly like that. Okay? Because we assume something that is our lamppost and then we build instrument and we search for it. You have to assume because we don't know what is dark matter, no? Getting it? So each assumption is like one lamppost, and one such assumptions, that's what I also spend some time, is called weak dark matter. Means we assume that dark matter may be weakly interacting. In nature there are 4 fundamental forces, gravity, electromagnetism, then strong nuclear force and weak nuclear force. If dark matter has electromagnetic interaction, then we would see them because electromagnetic interaction means photon. Getting it? But we don't see them. And dark matter, we know that it does not have strong interaction because strong interaction it will be ruled out, visible. Only option is if dark matter along with gravity. Of course, dark matter has gravitational interaction. That's why it changes the rotation. No, but along with that, it should also have. We assume that maybe dark matter is weakly interacting. That was a hope. Because if it does not have weakly interacting, we will never see it. Because to see in an instrument, it has to interact. You are able to hear me because you are interacting with me. The photon, the sound wave coming and the eardrum is vibrating. It's an interaction. So if it does not talk to visible matter, then how will you? So we hope that nature is not that cruel and nature will give us a glimpse that okay. So weak dark matter was proposed and there are many other things from particle physics. So they can be only detected in this way. Weak dark matter, if it is true, it actually does not interact so strongly. So it can passes through rocks, Himalaya mountain, mines. No, nothing can stop it. And that's why people built below 1.5 kilometer below the ground. There is a detector called liquid xenon detector. Xenon has huge atomic number, you know. So it's a huge 300 tons of xenon they put. And luckily it was in my Columbia University where I did PhD. I was not doing totally with that. One guy was doing PhD. He would go down by lift and his PhD was waiting for dark matter to hit this detector. If the dark matter hits here and if it recoils, he will get a Nobel Prize actually. So every day, every 1 month, he will come back to our institute because the experiment was much behind. He said, like, what are you doing? I am still waiting. So 1 year passed by, no hit happened. First year PhD done. Second year passed by, no hit happened. After 5 years, he got the amazing PhD because no hit has happened. And they rule out certain models because if it did not hit, that means you can tell that the number density must be very low. Because if it is huge in number, they will hit. So they give a constraint that okay, wind may be gone. Because if it has not hit, that means we don't know. We know that the probability is this much, and we expect 5 hit per year, but in 5 years there is no hit. With certain confidence, they ruled out, and he got a very amazing job in Chicago University professor because he did not get to see anything. So sometimes seeing nothing can be very important. It can rule out the things. So that is the case, and mostly this weakly interacting massive particle is gone. Now I work on something else called primordial black hole. Maybe dark matters are small marble-sized black holes. Recently, some newspaper also, one of my research also got international thing that we give a new idea that how primordial black holes are formed. And in solar system is a very small place compared to universe. No, so in our model, you get 6 to 7 small marble black holes in every solar system. That is a huge number actually in the galaxy. Getting it? So and then we showed that how some other people are working. If this small black hole, no, suddenly pass through sun, when black hole passes through, it will create hole. No, everything is sun. No, so there will be a tunnel, like you see tunnel under the mountain. You will see tunnel in the planet, tunnel in the. And in fact, there was another paper who said that in Jupiter or somewhere, if you see a small tunnel from one side to the another, that means a black hole has passed. Getting it? Of course, that will come down, bring down the thing, but there will be some mark of that. A small line will. Anyway, so this is very interesting that we don't know what black hole is. Now I'll go to a very interesting thing. So this is now I'm coming t equals to 0, close to t equals to 0. This is t up, this is 0.3 million years, and then above that 14 billion years is us. Now, do you know that once you go to very small distance, then normal classical mechanics does not work? How many of you know? What mechanics you need? Quantum mechanics. That's why atomic level classical mechanics does not work. In Rutherford model, if you just apply centrifugal, we will not be able to make the atom stable. Getting it? You need quantum mechanics. Getting it? So now, universe started from almost 0. So in the first 10 to the power minus 30 seconds or 10 to the power minus 15 seconds, it was actually all quantum mechanics. In quantum mechanics, one thing is very natural, that there is fluctuation. You heard about it, quantum fluctuation, means you cannot measure everything correctly. How many of you have heard about it, Heisenberg's uncertainty principle? Uncertainty principle, if you want to measure anything, you will see that there is answer, it is exact. In quantum world, if I was in a quantum world giving talk now, you will see Subinoy is giving talk, suddenly Subinoy vanishing, suddenly and you cannot see it because suddenly I see you gone outside the classroom and I am still talking. Everything is totally random in quantum mechanics, and that is the reality. Now, Even that time, that energy which was driving the expansion of the, I call it inflaton. No, we said Higgs particle like that, God particle, like an inflaton particle. That energy also very zigzag. There was fluctuation. That means if you measure density, some part will be high density, some part will be low density. You cannot get a smooth density because everything is fluctuating. Then universe expand, blow up suddenly, and this is 0.3 million years later. You see from our satellite that actually it is not smooth. There is fluctuation. And thank God that there is fluctuations. Because of this tiny fluctuation originating from quantum mechanics, you are here. Because suppose I give you exactly smooth universe, homogeneous. Can you clump into small star? Any point you take, the net force will be zero. Because every direction is the same. So even if you apply huge gravity, you cannot fragment it into filament if there is no initial fluctuation. Initial fluctuation means what? There is tiny over density and there is tiny under density. Now, if you apply gravity, what will happen? Over dense area will pull more gas into itself, and the under dense area will lose gas from itself. So that's why the initial fluctuation is so important. Otherwise, universe is so homogeneous, you cannot create any star. Stars means what? You have taken gas from the surroundings and clumped. But that means there has to be an initial seat of extra density. That's why it can bring more. Otherwise, you cannot bring. If it is totally homogeneous, you cannot break the symmetry and you cannot create anything. That's why scientists say thanks to quantum mechanics. Because in the first, after just space-time got created, the universe was governed by quantum mechanics and density was also fluctuating, and that got blown up, and then it became classical, but that over density and under density is there. Then gravity acts and you create beautiful. And now I will show you a simulation with audio. I don't know whether it will work. This is what we do. This is not my simulation, but we work with some supercluster computing group in Paris, similar. We also have our thing, but I show you because we didn't put our thing in YouTube. So this is what exactly you get. There is a tiny fluctuation, delta rho means over density of 10 to the power minus 5. Means mean density is same, but there is a very tiny fluctuation, and that grows. And if universe was not dominated by quantum in the beginning, then delta rho will be 0 and there will be no galaxy, and you will not be sitting here. So our origin is thanks to quantum mechanics. Okay, so now this is what exactly, before I show you the simulation, this is the tiny fluctuation 10 to the power minus 5. Then you wait 300 million years, this become bigger, the filament comes, because here it is almost homogeneous, then it become non-homogeneous, and then you see what happens. Okay. The music should come. See. So now it is homogeneous almost. Now you will see from computer simulation we mimic how gravity. If you zoom in now, sorry, this is the today's universe. It is exactly like filament, and each point is like galaxy cluster, and inside most of the space is empty. Okay. Now you zoom in, you see the galaxy. In each yellow dot, there are billions of galaxies. So you can go even deeper. Then you see. So now, even you are zooming in, now you will find our small Milky Way galaxy. So this, you are going in a smaller and smaller scale. That filamentary structure, now you are again zooming out, you will see this is how universe look from a large scale. By the way, if you look in our human brain, it exactly looks like that, neurons. So now, this simulation, you see, starting from time 0, you will see how galaxies. See, the over density become more over dense. These are voids, blues. Void say from void the things are getting moved to the clumpiness, and you see, this is the simulation we run in computer. Starting from cosmic microwave background 10 to the power -5 level of fluctuation, you rotate, you put it in the computer. It takes actually more 2 months. 5,000 computers runs together, 2 months, and you get these visible images. Okay. So this is video is in the YouTube, and you can navigate through the universe. No, now we are going in the smaller scale. Suppose you are going into the distance. So this is empty space, and one such tiny dot is our Milky Way galaxy. And within that Milky Way galaxy, there are 500 billions of suns. And then you are zooming in, flying through the galaxies in the computer simulation. Every dot is a galaxy. So you see that how many galaxies are there in the universe. Every galaxy has 500 to 600 billions of suns. And this is not the real, this is the simulation, but simulation is exactly the real. Okay, we matched it. Okay, so I'll not spend that much. So it's exactly random. It's not static at all. Everything is moving so fast. Galaxies are moving within themselves, and that's why two galaxies can even collide. In fact, our Milky Way galaxy close by is the Andromeda galaxy. They are actually coming, and after million years, they will collide. Okay, so there is huge randomness in the universe, but still there is orderliness. That's why life can come. Okay, so I'll take another 5-10 minutes for this part. The next half I'll use little bit of this and some board work. So this is the Nobel Prize who got the Nobel Prize by measuring the expansion rate. So how do you measure the expansion rate? By looking at the supernova. Why you look at supernova? Supernova has a property, type 1A supernova. Whenever they burst with same luminosity and same flow. So now you tell me, if I observe those supernova and if I see them dimmer, means they are fainter, that means those supernova are, because they cannot burst in faint glow. It is like all of them are 100-watt bulbs. But if you see one of the few bulbs are 100 watts are very faint, that means they are farther. That is why it is called standard candle. Because standard candle means they always have same glow, but if you see them dimmer, that means you can do the Flax law, no? 4 pi L square, how much energy is, and then you can connect how far are they. That's how we measure the distance. And that is how the Nobel Prize came. They were looking at further supernova. They know how far away they are because they know how dim or how faint they are. And they can measure their velocity also. And they found the velocity of the supernova is much higher than expected. And Einstein told that if something called dark energy in the universe, then he never expected. He mathematically said, then universe will accelerate. Space is expanding, but space will accelerate if there is dark energy. And that's what we found. And that got Nobel Prize. That's how we came to know that 70% is dark energy. And these are the tiny supernova. They always burst with same luminosity. And we match the density of dark energy because Einstein told how much dark energy you put, that will tell how fast universe expands. And we measure how fast universe expands. And before that, during my PhD, we thought it is dark matter and normal matter. But then Nobel Prize came up that there is 70% is even unseen there for energy. Matter is matter. Dark matter means a particle. But photon is not No, photon is like waves, like energy. So they are not particles, they are energy, and they are actually pushing the universe very fast. So I'll skip this. Actually, you can tell. Nobody knows what dark energy is. It is an all-pervading energy. It has a negative pressure, and fate of the universe depends whether universe will expand forever or again cycling universe, again big crunch will happen. It totally depends on the value of dark energy. And this video you will see.
The Big Bang giving rise to our universe is likely not a one-time event. Instead, the fuel not only generates our Big Bang, but it would also generate countless other Big Bangs.
That is the multiverse.
Each giving rise to its own separate universe, with our universe becoming but one bubble in a grand cosmic bubble bath of universe. And now, if we meld this with string theory, here's the picture we're led to. Each of these universes has extra dimensions. The extra dimensions take on a wide variety of different shapes. The different shapes yield different physical features. And we find ourselves in one universe instead of another simply because it's only in our universe that the physical features, like the amount of dark energy, are right for our form of life to take hold. And this is the compelling but highly...
So one thing, the astronomers has measured the Nobel Prize that what is the value of dark energy. It is very tiny, 0.120 and then 132. And you need this number for life to exist. And nobody knows that how some small number is there. Why? Because if dark energy, if you erase 2 zeros from here, that means you are creating dark energy 100 times more. That will push the universe so fast that even gravity cannot clamp the galaxy together. Because it is a competition. Gravity wants to bring things together and want to form star, and dark energy want to push things apart and thing apart. This balance, for that balance to happen, this small number has to be there. This is called cosmological constant fine-tuning issue. Then scientists ask, who fine-tune this? No, why so many zeros? And if you say, that doesn't matter, let me erase 2, 3 zeros, then you will be also erased. Getting it? Because this is a huge mismatch in modern cosmology. Mismatch is a huge trouble. That the constant, fundamental constant, as well as dark energy, it has to be exactly same. Otherwise, if you change the norm a little bit, you will see that you do the simulation, you will see no star can come. Getting it? So that much is now, and later, next part, I will do some mathematics and simple thing, and the video I will show you half video I have shown, and actually let's see the video. Then you will see. One second.
The Big Bang giving rise to our universe is likely not a one-time event. Instead, the fuel not only generates our Big Bang, but it would also generate countless other Big Bangs.
Other Big Bangs are happening as I showed you in the multiverse.
Each giving rise
and each has their own, each bubble is one universe.
But one bubble in a grand cosmic bubble bath of universe. And now, if we meld this with string theory, here's the picture we're led to. Each of these universes has extra dimensions. The extra dimensions take on a wide variety of different shapes. The different shapes yield different physical features. And we find ourselves in one universe instead of another simply because it's only in our universe that the physical features...
So our universe has this number. Other universe has other number. And we are lucky to have this number so that life can come.
A highly controversial picture of the wider cosmos.
And each universe gets a different number
now
of dark energy.
Seriously consider. In the very far future, those galaxies will rush away.
Now, if you wait for another
we won't be
1 million, 2 million, 3 million, or 4 million, 5 million years, the dark energy is taking over now. So everything is going upward from each other in a very high speed. Even all other nearby galaxies will also go away.
Widening gulf between us. So astronomers in the far future, looking out into deep space, will see nothing but an endless stretch of static, inky, black stillness.
So if you wait for 1 billion years and in Mysore, another scientist come and look for galaxies, but you will see in Cosmos project, they will show you many galaxies, which you observe, I showed you, billions of it, they will see nothing. Because of the dark energy, even the nearby galaxy will be thrown away. And they see our papers of cosmology, they see that we are publishing paper with 500 billion galaxies, this thing. They will say like, what stupid guys were they? Because they see there is nothing, because they are also true, we are also true. Because in between, the dark energy has thrown everything. So we are living in a very special time, even in the history of cosmos, where you can see the beautiful universe. If you are born 5 million years later, you will see only Milky Way. Other has gone away because of dark energy. Okay, so that much now. Next one. You have any questions? Anything? You can ask any question. Don't get afraid. Okay. Stupid, not stupid, anything. Okay. Yes.
Since the universe is never ending, then how can you estimate the visible thing is 4% and other things are?
Because it is homogeneous and the density in the local universe you measure, that is true for everyone.
Sir, you said it is homogeneous, but in the video right now you said one galaxy is having different number of dark matter and another galaxy is having different percentage of dark matter.
No, every galaxy has same percentage of dark matter, but universe is not homogeneous in solar system or galaxy scale. See, if you take a water jar, if you see from far, you see homogeneous water, isn't it? But if you take microscope, you go, then you see that the intermolecular distance is not homogeneous. So exactly in small distance it is not homogeneous because the solar system is not homogeneous.
Once we don't know what is beyond some distance, then how can we estimate that this percent of visible?
No, up to CMB we are measuring that distance, but huge distance, almost from cosmic microwave background till now, light is traveling. We have measured billion light year distance. The data is from billion light years. What you are seeing, I saw the galaxy is the simulation, but we have data from billion light years. That's the magic. You don't need to see now because the light is still traveling. So we have data from, because if photon is traveling from cosmic microwave background time, it has traveled 14 billion years. So we see from CMB that how much is dark matter, how much is dark energy. It's little technical, but it's not that we don't see them. We see the huge universe. Okay.
Sir, as a researcher, what's your view on parallel universe?
So parallel universe depends on the hidden dimension. I did not show you the last May. He showed that there are hidden more dimensions. String theory says. So if there are more dimension, here is our 3 dimension, no space and 1 time. But if suppose in this room there are other 6 dimensions, then there will be other universes. So, but we cannot see them. So in string theory there might be parallel universe, which might be true. Okay, but from physics point of view, we cannot see them. No connection. Only gravity may connect up. Because if you have seen interstellar movie, only gravity could connect to them. Because gravity is permeable to everything. That's why dark matter is only talking to us through gravity. Dark energy is only talking to us through gravity. So like that.
I have one more question.
Yeah.
You said that universe is initially maybe contracting and not the expanding. So here we don't know the time scale. We are considering it to the decline.
So before that we don't know.
So is that mean that are we in the loop?
There is a prediction if that guy from Princeton, they said, if it has contracted before and then it is expanding, then there will be some visible signature that we did not see. So it's not that we don't know that whether, but if it is true, we are in a loop. A loop means it is infinite. No, it can continue forever. Circle can continue forever, but linear is not.
And one more question. You said you are working on nuclear. So does there any theory just Cartesian, the string theory is support? So string theory
and it has given model of inflation. That's many string theorists are working on that. It's not that we just assume. They can tell that what energy in the beginning gave rise to that super expansion of the.
Is it something like a particle?
No, it is an energy. It is not like dark energy. It is another energy. It is not particle.
So it is also real.
Real like particle. See, every in physics, every particle, if you go deeper, they can be energy also because physics, the particle and energy can. But here they are not in the particle form. These are pure energy form. You cannot localize them in a point.
Because they can say that imaginary masses, maybe
A tachyon, all these things. So tachyon also come in that field. There are some model of tachyonic inflation. In field. Any more? Yes.
नमस्कार আমি জগন্নাথ বলছি বাংলা থেকে
Okay.
আইআইটি খড়গপুর থেকে ছাত্র 82 to 84 I did my MTech IIT Kharagpur
Yeah.
joined ISRO
Yeah.
served 32.5 years. I'm now making an effort for postdoctoral work. It's on mythology on life in cosmos and exoplanets. I'm trying to search out some of the sutras of different great religious scriptures. In a simple way, I want to answer from you. The Jnana Yoga, Karma Yoga, there are different forms of mythological interpretations of the world. How far it is validated?
This part I am not expert, but some Western physicist has talked about some. I don't know about this yoga you were talking about, but they said that some philosophy that time is circular and the space and time they have. Even Schrodinger, the father of quantum mechanics, has quoted that he got inspiration of quantum mechanics from this. But I don't know. But there is no mathematical analogy yet. But some people are inspired that thing. But it's also personal thing. But it has not come into the mainstream physics yet. It may come. I don't know. Yes.
It's really metaphysics.
Yes, metaphysics. So when it comes to metaphysics, you cannot do the mathematics. So many physicists also leave it there. They don't. Physicists also say, "I don't know," means what is true. Yeah.
If there are no further questions, we can take a break. And then, when my what's the report?